Okay, so in this video, we will consider example of differentiation involving exponential and logarithmic functions. If you remember, there was a very special case of the exponential function base e, where e was approximately 2.71828, and the derivative of e to the x is e to the x. The inverse function was ln of x, and the derivative is 1 over x. The only difference when you have a change of base, the derivative of any exponential function is the function itself times the ln of the base. The derivative of any logarithmic function is 1 over x times the ln of the base. Let's consider a few examples involving our basic rules of differentiation and logarithmic and exponential functions. Let's start with a few examples of the chain rule. What if I ask you for the derivative of e to the x squared, let's just go with that, or x squared plus 1, say. Right, this is the exponential of x squared plus 1. So if you think about it, well, if I give you a value of x, you would first square it, then add 1, and then you would exponentiate e to this power. So here we have a composition where the outside function is the power e. The exponential will be the last thing we would compute. And by the chain rule, we have to differentiate the outer function first, which is the exponential, and you see the derivative of the exponential is itself. So we'll get e to the x squared plus 1. That only takes care of the outside function, so we scratch off the e. We have now differentiated it, but then the chain rule says if there's something left over, we have to multiply what we have so far by the derivative of what's left over. What's left over is x squared plus 1. The derivative of this is 2x. Differentiated, scratch out. There's nothing left over. So if we write 2x first, we'll have 2x e to the x squared plus 1. And that's the derivative of e to the x squared plus 1. 2x e to the x squared plus 1. What if we change e, say, for 3? The derivative of 3 to the x squared plus 1. Well, once again, if I give you a value of x, you would first square it, then add 1, and then take 3 to this power. So the outside function is the exponential function base 3. The derivative is the same thing times ln of the base. So we get 3 to the x squared plus 1 times ln of the base, which is 3. But that is only the derivative of the outside function. The chain rule says we have to multiply by the derivative of what's left over, which is x squared plus 1. The derivative is 2x. So if you rewrite the constants first, we'll have 2 ln of 3 times x times 3 to the x squared plus 1. What if we had the ln of x squared plus 1 and wanted the derivative of that? Well, we differentiate ln of x squared plus 1. Once again, we have a composition. Right? If I give you a value of x, you will first square it, then add 1, and then take the ln of the expression. So the outside function is a ln, and the derivative of ln, if you look at it, the derivative of ln of something is 1 over that very same thing. So we differentiate ln here, but what's inside is x squared plus 1. So we'll get 1 over x squared plus 1. That's the derivative only of the ln, cross that out, times what's left over. The derivative of x squared plus 1 is 2x, so times 2x. We can combine as a single fraction, and we have 2x over x squared plus 1. What if we had a different base for a logarithmic function? What if the base was not e? What if the base, say, was 5? So what if we ask for the derivative of the logarithmic function base 5 of x squared plus 1? Well, the outside function is once again the logarithmic function, and you see the derivative of any logarithmic function will be 1 over the argument. To differentiate this logarithmic function, you have 1 over the argument, 1 over x squared plus 1. But don't forget that it's 1 over the argument times the ln of the base. The base here is 5, so it's x squared plus 1 times the ln of 5. And this takes care of the derivative of the logarithmic function base 5. But there's still x squared plus 1 left over. By the chain rule, we have to multiply by the derivative of x squared plus 1, which is 2x. So we are left with, in the end, 2x over, if I put the ln of 5 first, ln of 5 times x squared plus 1. And that's it. This is how you differentiate with exponential and logarithmic functions in the case of the chain rule. Let's consider just a few other examples. What if we throw in there some trigonometric functions? So what if I ask you the derivative of, say, e to the sine of x cubed? Once again, we have a composition. If I give you a value of x, you will cube it, then take the sine of it, and then take the exponential. So we differentiate the outside function first, which is the exponential, but the derivative of the exponential function base e is the same thing, so we'll get e to the sine of x cubed. And that takes care of the base e. But there's still sine of x cubed left over, so times. And now once again we have a composition. Sine of x cubed. The sine is the outside function. The derivative of sine is cosine. Cosine of what? Of what's left over, x cubed. But there's still x cubed left over. The chain rule one more time. Times the derivative of x cubed, and that is 3x squared. There is nothing left over, so we are done with the differentiation. And usually, as always, we write the simplest terms first, so we'll write this as 3x squared times cos of x cubed times the exponential function of sine of x cubed. So there you go. What if we had examples where we throw in some logarithms, but before we have to differentiate, we should simplify first? Let me give you just one example before that. What if we asked for the derivative of ln of x, say, over x? Now we have a quotient, so we use the quotient rule. The derivative of ln of x is 1 over x times the bottom, x, minus ln of x times the derivative of the bottom, which is 1, over x squared. Well, this simplifies because 1 over x times x is 1, and we have 1 minus ln of x divided by x squared. There you go. What if we have a product rule involving, say, another logarithmic function? So what if we had the derivative of, say, log base 2 of 3x plus 1 times, say, cosine of 5x? Well, we have a product, so we have to use the product rule. The first function is the logarithmic function base 2 of 3x plus 1. The second is cos of 5x. Derivative of the first function. We differentiate the log, so we get 1 over the argument, 3x plus 1, times the ln of 2. Chain rule times the derivative of 3x plus 1, which is 3. I can put the 3 on top. So that's the derivative of log times the second function, so cosine of 5x. But that's only half of it, right? So plus, I'm running out of space here, so I'll just write the plus here. So plus the first function, log base 2 of 3x plus 1, times the derivative of, now the second function. Once again, we have a composition, cosine of 5x. We differentiate the outside function. The derivative of cos is negative sine, so times negative sine of 5x. But that's just the derivative of cosine times the derivative of the inside, which is 5. And there you have it. This is the derivative of log base 2 of 3x plus 1 times cosine of 5x. If we rearrange a little bit, we'll have 3 cos of 5x over 3x plus 1 ln of 2 And here we'll have a minus 5 sine of x, sine of 5x. So minus 5 sine of 5x times the logarithmic function of 3x plus 1 base 2. And this is it. And again, this works, with everything's the same as before, except remember that we have these 4 differentiation formulas. Let's consider now just 2 examples involving a logarithmic function where before differentiating, we are better off simplifying first using the basic properties of logarithmic functions. So what if I gave you a quotient? And I said find the derivative of the ln of, say, 2x plus 1 to the 4th power over x squared minus 3 to the power of 8. Now if you differentiate this directly, you would have the derivative of ln, which is 1 over this inside, times the derivative of the inside, which would involve a quotient rule and a chain rule on top and on the bottom. But if we simplify before we differentiate, we can save ourselves a lot of work. So remember the first property here. The ln of a quotient is the difference of the lns. So if I give you ln of a over b, that's just the ln of a minus the ln of b. So we can apply this property first before we differentiate. So we keep the derivative there. We're still not differentiating. But now we have the ln of this over the ln of this over this. So ln of a over b, this is what we have. This will be the ln of the numerator, 2x plus 1 to the 4th power, minus the ln of the denominator, x squared minus 3 to the 8th power. Well, we could differentiate this, but we can even do better. We have yet another property of logarithmic functions. If I give you the ln of a to the b, we can move b outside of the logarithm. And this comes up to b ln of 8. So, again, we don't differentiate. We simplify one step further. So we'll move the 4 outside, and you see the reason why this is so nice is the power of 4, which would cause us one more application of the chain rule. After we move the power of 4 outside, it becomes a scalar multiple, which makes the differentiation a lot simpler. So we have 4 ln of 2x plus 1 minus 8 ln of x squared minus 3. And now we can differentiate, and you'll see we will have a much easier time than if we had found the derivative right from the get-go without simplifying. So let's go ahead. 4 is a constant multiple, so it just stays there. We differentiate ln. The derivative of ln is 1 over what's inside, so times 1 over 2x plus 1. Chain rule times the derivative of the inside, which is 2. That takes care of the first term. Minus 8 is a constant multiple, so it just stays there. Derivative of ln is 1 over what's inside, x squared minus 3. Chain rule times the derivative of this, which is simply 2x. And that's it, we're done. This is the derivative. Well, we can at least clean this up a little bit. This will give us 8 over 2x plus 1. Minus, you could have factored in 8 here, but let's not bother. Minus 16x over x squared minus 3. And there you have it. And if you don't think this was nice, try out the derivative of this expression directly without simplifying first, and you'll see it's a lot more work. And you'll have to do also a fair bit of algebra to simplify to this function right here. What if we had, say, a product instead of a quotient, and we'll have a product, say, of 3 terms? And we can recall right here that the ln of a over b is ln of a minus ln of b, but the ln of a times b is just the ln of a plus the ln of b. And this is true of a product of three terms. If you add the ln of a times b times c, it would be the ln of a plus ln of b plus ln of c. So let's figure out now this example, and this will be our last example for this video. What if we asked for the derivative, and you see if we had changed the base, if it wasn't the natural logarithm, just ln but log base a, the only difference here is that we would have 1 over the ln of the base, and the same thing here. And that's the only difference. So if you can handle derivatives with the exponential function base e or the logarithmic function base e, if you change the base, it's just a multiple of the ln of the base. So it's really not that different. So what if we add the ln, and we'll take, say, the square root of, let's go with cos of x, times e to the, let's go with tan of x, times, say, let's go with ln of x. Why not? So now again we could differentiate this as 1 over all of this times the extended product rule on this product of three terms. But this would be again a lot of work. So first we will expand the logarithm. We have a ln of three different things. So again, we do not differentiate yet. We will rearrange the expression. So derivative of ln of this times this will be ln of the first term. So ln of the root of cosine of x plus the ln of the second term, ln of e to the tangent of x, plus the ln of the third term, so plus the ln of x. And now two things we can do here. We can rewrite the square root as a power of 1/2. So this is cos to the 1/2 power. And again, with this property of the logarithmic function, we can move the 1/2 power outside the logarithm. This will save us once again an application of the chain rule, which is always a good idea. So once again, we don't differentiate yet. We simply rewrite, pull the 1/2 after replacing the square root by a 1/2 power outside, and you'll have simply 1/2 the ln of cos of x. Here, the ln is the inverse function of the exponential function base e, so the ln cancels e, and we're left with quite simply tangent of x. And ln of x, this is basically it, so it stays ln of x. And now we can differentiate. And once again, we'll have a much easier time with the derivative of this form instead of the derivative of this form of the function. If you don't believe me, we'll differentiate this directly and then be your own judge. And I hope you'll see that this actually gives you a much nicer solution. So we differentiate the first function. 1/2 is a constant multiple. It just stays there. The derivative of ln is 1 over what's inside, so times 1 over cosine, times the derivative of the inside. The derivative of cosine is negative sine. And that takes care of the first function. Plus the derivative of tan of x. The derivative of tan of x is secant squared of x. That takes care of this function. Plus, now here we have a composition of, well, two compositions. Ln of, the derivative of ln is 1 over what's inside, so 1 over ln of x, times the derivative of ln of x, which is 1 over x. We can clean this up a little bit. If you look at the first term, we have sine of x over cos of x. Well, this is by definition tangent of x. So all we're left with is negative 1/2 tangent of x plus secant squared. This is as good as it gets. And here we can write this again, the simplest term first, as 1 over x ln of x. And there you have it. The derivative of the ln of this rather nasty product is just negative 1/2 tan of x plus secant squared of x plus 1 over x ln of x. So every time you have the derivative of the ln of something, you see the first case, we have the ln of this big quotient. Second case, the ln of this big product. Never differentiate directly. Don't be too hasty. Always ask yourself, using the three fundamental properties of logarithms, this one, and this one, always ask yourself if you can rearrange the expression so that once you've rearranged it, you will have a much easier time differentiating. And this is how you should always proceed. Always never be too hasty. Try and simplify the expression first, and only then find the derivative. In our next video, we will consider functions that cannot be differentiated directly with our usual rules of differentiation. And what will be really interesting is, using the ln function, the logarithmic function base e, we will be able to find the derivative of these functions using also implicit differentiation. And this will be our next topic, which we will call logarithmic differentiation.